1801 1851 Unit 3 Magnetochemistry by Dr. Devang R. Pandya, Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. These are the syllabus points, and out of this syllabus points, some points we're going to discuss in today's lecture. Magnetic susceptibility and basic derivation of diamagnetic susceptibility. This is a direct point, but before that, we need to discuss different terms associated with magnetic properties or magnetochemistry. So that terms we will going to discuss first, and then we're going to discuss the magnetic susceptibility and basic derivation of diamagnetic susceptibility. Next, we need to discuss Pascal constant and its utility. So these 2 points today we are trying to cover in this lecture. Curie's law and Curie-Weiss law, then antiferromagnetism and ferromagnetism. Next, type of antiferromagnetism. Antiferromagnetic exchange pathway. There are two antiferromagnetic exchange pathway we need to discuss. Direct metal-metal interaction and indirect metal-metal interaction, in which we are going to discuss super exchange mechanism. So this is the syllabus for Unit 3 Magnetochemistry. Magnetochemistry is the study of magnetic properties of materials. By magnetic properties, we mean not only whether a material will make a good bar magnet, but whether it will be attracted or repelled by a magnet. So that property we need to discuss today. This includes synthesis, analysis, and understanding. This short description is meant to give a basic understanding before you delve into a more complex treatment in magnetochemistry. Magnetism arises from moving charges such as an electric current in a coil or of a wire. When wire is coiled, an electron is going to move in that coil, it will give rise to the magnetism. In a material which does not have a current present, there will still magnetic interactions. Atoms are made of charged particles like proton and electron, which are moving constantly. Magnetic effects arise mainly from the electrons in a molecule because the magnetic moment of an electron is about 10⁻³ times that of the proton. The process which create magnetic field in an atom are: number 1, nuclear spin, which some nuclei such as a hydrogen atom have a net spin which creates a magnetic field. Number 2, electron spin. An electron has two intrinsic spin states, upward, downward, clockwise, anti-clockwise, similar to the top spinning, which we call up and down, alpha or beta spin. Third, electron orbital motion. There is a magnetic field due to the electron moving around the nucleus. So these are the three matters through which magnetic property arise or magnetic field generate in any material. Now, why we need to study magnetochemistry? What should be the importance of learning this magnetochemistry, or what would be the outcome of magnetochemistry? The past few years have seen magnetic susceptibility take its place along with dielectric constant, electron diffraction, X-ray diffraction, and molecular and atomic spectra as one of the most powerful tools at the disposal of the chemist. Magnetism are critical to an understanding of the NMR, nucleomagnetic resonance, and ESR spectra of transition metal ion complexes. Now let's define the magnetochemistry. Magnetochemistry is the application of magnetic susceptibilities and of closely related quantities to the solution of chemical problems. So in this magnetochemistry, there are certain different terms used. We need to understand those terms before we need to study the complex theories of magnetochemistry. First is a pole strength. The strength of a magnet may be expressed in terms of a unit pole. A unit pole may be defined as one that repels or attracts a similar pole placed 1 centimeter away with a force of 1 dyne. Thus, a unit intensity of magnetic field exists at the point the unit pole experiences a force of 1 dyne. So that is how we can define the pole strength, a strength of magnet, and that can be expressed in terms of a unit pole. That means when a substance attracts or repels similar pole placed 1 centimeter away, that is the distance, with a force of 1 dyne, then that is considered as the pole strength of that magnetic material. Now, pole strength and line of forces. A magnetic field of unit intensity is taken to give a unit line of force per square centimeter. If a pole of strength M is enclosed in a sphere of radius 1 centimeter, a total of 4 pi m lines of force will emanate from the pole. The surface area of the sphere being 4 pi square centimeter. This is Gauss law. The number of line of force per square centimeter at the surface of the sphere is given by pole strength and line of force. That can be represented as 4 pi m divided by 4 pi is equal to m. Intensity of magnetization, another term. The intensity of magnetization I, induced in a body by an applied magnetic field is expressed in terms of the pole strength induced per unit area. I is equal to m by A, where m represents the magnetic field, A expressed the induced unit area. This is the situation for a hypothetical monopole, single pole. For a magnetic dipole of length L and area A, we can write this equation as I is equal to m into L divided by A into L, and that is equal to magnetic moment divided by volume. So intensity of magnetization is the magnetic moment divided by volume. Thus, intensity of magnetization may be alternatively defined as the magnetic moment per unit volume. Now, magnetic induction, another term. When a body is subjected to a magnetic field of strength H, where H lines of force acting per unit area, the total line of force coming out per unit area of the body is given by the sum of H and an additional field delta H due to the induced magnetization. So up to the strength H, that is magnetic power intensity, and then if little extra delta H value is going to be obtained, that is considered as induced magnetization. The magnetization because of the magnetic field of strength, little induced, that is represented as delta H, and it is called magnetic induction. Since I represent the pole strength induced per unit area, we can write B magnetic induction is equal to H plus delta H, the extra magnetic power generated on the substance which is placed in a magnetic field, is equal to H plus 4 pi I. We can further write this equation as P magnetic permeability is equal to B by H is equal to 1 plus 4 pi into bracket I upon H. Magnetic permeability is therefore the ratio of density of line of force within a body and that is under vacuum. Now, magnetic susceptibility, a very thin barrier between magnetic permeability and magnetic susceptibility. So, we are now going to focus our main topic, that is magnetic susceptibility, after learning different terms associated with magnetic susceptibility. The ratio of I by H in equation 1.5, we have already seen in the slide before, is the magnetic moment per unit volume per unit magnetic field and is known as the volume magnetic susceptibility kappa of the body. This is the symbol of kappa. It is a characteristic properties of a compound. We know that I proportional to H. This is a proportionality symbol that you need to understand. It should be brought infinite symbol, but it is used for proportionality, intensity proportional to the magnetic field. Therefore, I is equal to, when intensity is due, proportionality is removed, we need to put a constant, that is kappa H, and therefore kappa is equal to I by H, that represent the magnetic susceptibility. The magnetic susceptibility may be conceptually treated as the response of a substance to induce magnetization in any compound. Gram susceptibility, it is given by psi z is equal to kappa by rho or xi v by rho, where rho is the density and kappa or xi v is the volume magnetic susceptibility of the substance. Molar susceptibility, it is expressed as psi m is equal to psi z into m, where m is the molar weight of the substance. So when molar weight is multiplied with the gram susceptibility, it is turning to molar susceptibility. Now, turning effect on magnetic dipole. Magnetic moment, another term we need to discuss. In a discussion on magnetochemistry, the magnetic susceptibility hardly used because of the unwieldy figure. A more convenient property is the magnetic moment. Taking Sn as a magnetic dipole of length L and field H as the strength of the applied magnetic field, we can see here the strength of the applied magnetic field is in this direction. We can write turning moment of the couple is equal to force into distance. The force into distance is equal to mh into pn is equal to m into hl sine theta, mlh sine theta, or either it can be represented as mu h sine theta, where mu is equal to m into l. When 90 degree, the turning moment of the couple is mu h. Thus, mu h is a measure of the work done by the magnetic field in rotating the magnetic dipole by 90 degree from a position perpendicular to the h to one parallel to h. So here you can see that the previous figure, this is the h. Now it is in a perpendicular direction. We need to move to 90 degree so that from perpendicular it turns to parallel direction. Parallel to h. The parallel ml gives the magnetic moment mu of the substance that we can see in the previous diagram. That is this value. Parallel will going to give the value of the mu, m into L. It may be noted that it is the magnetic susceptibility of a substance that is determined experimentally. The magnetic susceptibility is then converted to the magnetic moment with the help of Curie equation. That Curie equation we are going to learn in the next theory. It should also noted that the magnetic susceptibility is an additive property, whereas it is the square of the magnetic moment that is additive. The relation P is equal to 1 plus 4 pi kappa easily predict two classes of magnetic bodies. When P is equal to 1 in this equation, evidently we are talking of a vacuum. Kappa is equal to 0, B is equal to H. When kappa is negative, susceptibility is negative, we have P less than 1 and the substance is called dimagnetic. Such a substance allows a similar number of line of force to pass through it as compared to that in the vacuum, and therefore refers to move to the region of the lowest magnetic field strength. On the other hand, when kappa is positive, that is positive magnetic susceptibility, P is greater than 1, and we have a paramagnetic substance. Such a substance allows more lines of force to pass through it and therefore prefers to move to the region of the highest magnetic field. So here you can see that when value of kappa is negative, we have P less than 1. Substance is called to be dimagnetic, that is this dimagnetic. Such substance allows a smaller number of line, 1, 2 and 3. Smaller number of line pass through it, and when kappa is positive, P is greater than 1, the substance is paramagnetic. So paramagnetic substance when placed in a magnetic field, it allows more lines. 1, 2, 3, 4, 5, 6. Here 3 and here 6, almost double line passing through the substance, which proves that the substance is paramagnetic in nature, and this will repel the passing magnetic line of force, and due to that less number of line passing through the substance, it is considered as dimagnetic. Paired electron always repels, unpaired electron may little favor to the attraction, and that is why more number of electron lines are passing through the paramagnetic material and less number of lines are passing through the dimagnetic material. The type of magnetic bodies in which when a paramagnetic substance is drawn into a strong magnetic field, placed into a strong magnetic field, it takes up a position parallel to the field. Align itself with the field. We can consider that the substance which converted parallel to the applied magnetic field, that substance is of a paramagnetic in nature. If we treat a paramagnetic substance as a micromagnet, its north pole will face the south pole of the applied magnetic field, whereas its south pole will point towards the north pole of the applied magnetic field. As you know that opposite poles attract each other, and as a result, when we place a paramagnetic substance into a applied magnetic field, then the south pole of paramagnetic substance attracted towards the north pole of applied magnetic field, and north pole of paramagnetic substance attracted towards the south pole of the applied magnetic field. On the other hand, when a dimagnetic substance is placed in a magnetic field, it gets oriented at right angle to the applied field. It tends to withdraw from the field. That means it will neither attracted towards north or south pole. Instead, it will remain perpendicular to the applied field, and therefore it tends to withdraw from the field. That indicates the repulsion rather than the attraction. In most paramagnetic substances, the magnetic property originates entirely from the individual magnetic centers. There is no secondary magnetic interaction between the neighboring magnetic centers. Such a substance is called magnetically dilute substance. There are some paramagnetic substances in which the secondary magnetic interaction exists between the neighboring magnetic centers. Such a substance is referred to as magnetically concentrated. Now these are the terms that you need to remember. Magnetically dilute substance, that is also from the paramagnetic substances, and magnetically concentrated substance, that also obtained from a paramagnetic material, and the interaction in it may lead to either a decrease or increase in the magnetic moment. A substance of type 1, that is decrease, is called antiferromagnetic, and a substance is of type 2, that is increase in magnetic moment, it is designated as ferromagnetic material, that we can see in a figure. Here you can see that a substance which is a paramagnetic in nature will, when we do the plot of magnetic susceptibility versus temperature, magnetic susceptibility versus temperature curve indicate that if there is a gradual increase as the decrease of temperature, magnetic property increase, substance is considered as paramagnetic in nature. But at particular temperature, which is either known as Curie point or nil point. When paramagnetic material is provided less temperature and it reach to a point of temperature from which the value get decreased, magnetic property get decreased, the material act as antiferromagnetic material, and the point of temperature from which the magnetic property decrease, it is known as nil point or nil temperature. And if the substance, paramagnetic substance, when will going to decrease the temperature at one point of temperature from which the magnetic property get increased, then that substance act as a ferromagnetic material, and the point of temperature from which this magnetic property get increased is known as Curie point. So magnetic susceptibility versus temperature bifurcate paramagnetic material into two classes, ferromagnetic and antiferromagnetic, depending on this 2 point of temperature, Curie point or nil point. From Curie point, if the magnetic property of the substance increases at lower temperature, it is ferromagnetic, and from nil temperature, if the magnetic property of a substance decrease, then it is considered as antiferromagnetic material. So paramagnetic can be ferromagnetic or antiferromagnetic. The condition is at Curie point or nil point, its behavior must get deviated from the magnetic property of the paramagnetic material. A diamagnetic substance has its magnetic susceptibility invariant to temperature. That means if we have a diamagnetic substance and we're going to increase or decrease temperature, there is no change in the behavior of the substance, then it is considered as diamagnetic substance, because its magnetic susceptibility is invariant to any temperature, whereas the magnetic susceptibility of a paramagnet follows an inverse relationship with temperature. That means when temperature increase, magnetic property decrease, and when temperature decrease, magnetic property increase. An antiferromagnet has a characteristic nil temperature above which it behaves like a paramagnet, but below this temperature its magnetic susceptibility decreases with increasing temperature. That we have always already noticed in this diagram. From nil temperature it behaves like paramagnetic material, and below nil temperature, as the temperature increase, magnetic property get decrease. A ferromagnet has a characteristic Curie temperature, that is indicated as Tc. This one is indicated as Tn, above which it behaves like a paramagnet, but below this temperature its magnetic susceptibility increase rapidly. The majority of coordination complexes are magnetically dilute. Now, we have gone through what is magnetically dilute. As in these complexes, the paramagnetic centers are usually linked to ligands where the donor atoms are reasonably separated from each other by other atoms. As a result, no secondary magnetic interaction is possible between the neighboring paramagnetic centers. Of the magnetically concentrated coordination complexes, most are antiferromagnetic and very few are ferromagnetic. Antiferromagnetism may arise via one, that is metal-metal interaction, which we will going to learn into the exchange pathway, as in Mn2CO10, and the super exchange, that also we are going to study in the last part of this unit, through one or more bridging atoms like oxygen, nitrogen, fluoride, chloride and sulfide. As in many copper 2 oxovanadium 4 and oxomolybdenum 5 complexes of tridentate dibasic O and O donor skip bases, for example N hydroxyphenyl salicylamine is the example for this antiferromagnetism and its activity rise in such kind of complexes. Well, here is the table given for these different magnetic bodies. Dimagnetic material, paramagnetic. Paramagnetic may show ferromagnetism and antiferromagnetism. Ferromagnetism at Curie temperature, antiferromagnetism at nil temperature. Now, these are the types caused by dimagnetic. Paired filled shell electrons, that is paired electrons. The effect is submerged by an unpaired electron spin, and the magnitude of Gi, that is gram magnetic susceptibility, negative or small, that is -1 into 10 raised to -6 CGS unit. And as far as temperature field dependence of gram magnetic susceptibility is concerned, dimagnetic materials are independent of field as well as the temperature. The example of the compound act as dimagnetic material substances, that is H2O, KCl, potassium chloride, organic ligands which have paired up electrons. Now, paramagnetic material, that is caused by unpaired electron spin and orbital rotation or motion. The magnitude of Gi, that is gram magnetic susceptibility, is approximately 10 to 100 into 10 raised to -6 CGS unit. As far as temperature and field dependence is concerned, it is field independent and varies inversely with the temperature. The example for paramagnetic complexes are hexaquachromium sulfate, ammonium hexaquamanganese sulfate. These are the example of paramagnetic complex. Now, ferromagnetic material. Here also, because ferromagnetic material and antiferromagnetic will from paramagnetic material only, but at Curie temperature it will increase the magnetic property, then it is ferromagnetic, and at nil temperature when it decreases the magnetic property, it is antiferromagnetic. So here also unpaired electron is required. Neighboring particles with unpaired spin interacting among themselves act as ferromagnetic material. The value of gram magnetosusceptibility is positive and it should be very large, approximately 10 raised to -2 to 10 raised to 4 into 10 raised to -6 CGS unit. Above Curie temperature, the magnetic susceptibility varies inversely with temperature T, but below Curie temperature, the gram magnetosusceptibility arises abruptly dependent on the field. Most example is metallic iron piece, which act as ferromagnetic. So if you have an iron piece and if you are going to put it into magnetic field, that iron piece itself act as magnet, that indicates ferromagnetic behavior. Now antiferromagnetic, and thus formed a ferromagnetic, if we are going to put into high temperature, the magnetic behavior get decrease. So that you have always, you can notice at your home the Curie temperature for ferromagnetic material. Now antiferromagnetic material, neighboring particles with unpaired spin interacting among themselves. The value of gram magnetic susceptibility is positive but very small, not very large. So it is between 0.1 to 10 into 10 raised to -6 CGS unit. Above nil temperature, the gram magnetic susceptibility varies inversely with temperature, but below nil temperature, The ground magnetic susceptibility decreases, and it may depend on the applied field. Both this dependent on the applied field, while this one is independent of the applied field. That is the difference between paramagnetic, ferromagnetic, and anti-ferromagnetic. Examples are copper 2 acetate monohydrate, some skip base complexes of copper 2, oxovanadium, and oxomolybdenum complexes act as antiferromagnetic material. Now this is the various type of magnetic behavior of a substance, which already we have discussed: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic. 10 raised to minus 6 EMU unit, 0 to 10 raised to minus 4. This is common. This is in depth, previous table, and this one common general trends we will going to obtain: minus, plus, plus, plus. That is the sign indicated for this different magnetic behavior. These are the value in which we will notice the magnitude of these different substances. And as far as field dependence is concerned, diamagnetic and paramagnetic field independent, while ferromagnetic, antiferromagnetic field dependent. Field induced pair electron circulations is the reason to show dimagnetism. Angular moment of electron is responsible for paramagnetism. Spin alignment of dipole-dipole interaction of moment on adjacent atoms, two atoms when come closer and they are having unpaired spin, so parallel spin arrangement will going to give ferromagnetism, and anti-parallel spin pairing of dipole-dipole interaction or two different atoms will going to generate antiferromagnetism. Now, two sources of paramagnetism: orbital and spin effect. An electron has two motions associated with it. One, it's going around the nucleus in an orbit, that is orbital rotation. Taking the classical picture we are going to show you later, since the electron is itself charged, this orbital rotation is equivalent to the movement of a charge along a loop, which generates a magnetic field perpendicular to the plane of the orbit. The other motion is the spinning of the electron about its own axis, which too is equivalent to the movement of a charge and generates a magnetic field. Rigorously speaking, the electron spin does not have any classical analogues. In the orbital and spin effect, you can see that this is the orbital rotation of electron. This O represents the nucleus. Orbital magnetic moment. Let us assume that a single electron of charge E, that is this one, and mass m is moving about nucleus O, this is nucleus, with an average angular velocity, that is omega. That is angular velocity of the electron with charge E moving in this orbit surrounding nucleus O. The number of revolution per second the electron makes is then omega by 2 pi. That is the number of revolution per second this electron is making surrounding this nucleus O. The current is carries per second is E omega by 2 pi c, where c is the velocity of light, EMU, electromotive unit. According to the principle of electrodynamics, such an orbiting charge, that is moving charge in orbit, generates a magnetic field whose magnetic moment is given by orbital magnetic moment, and that is equal to strength of the current into area of orbit. Now, strength of current, that is E into omega by 2 pi c into area of orbit, that is pi r square, and that is directional, so vector is there. Since c is the velocity of light and r square vector is the mean square radius of the orbit. It is represented as, that means orbital magnetic moment is represented as E omega r square by 2c. Such a relation has little utility if it cannot be expressed in a form that includes the quantum number characteristic of the electron movement. An electron has a characteristic angular moment which is expressed as orbital angular moment quantum number L, secondary quantum number, azimuthal quantum number L. As we know, the orbital angular moment is equal to m omega r square is equal to L into bracket L plus 1 whole raised to 1 half, that means in square root, into h upon 2 pi, where h is the Planck constant. So the orbital magnetic moment mu L is given by mu L is equal to E omega r square by 2c is equal to L into bracket L plus 1 bracket over raised to 1 upon 2, that is under root square root EH by 4 pi mc is equal to L into bracket L plus 1 raised to 1 half beta, where beta value would be EH by 4 pi mc. When the appropriate values of the substituted values are substituted in this equation, we find that beta, that is Bohr magnetron's value, is equal to 0.92731 into 10 raised to minus 20 arc Gauss inverse 1. So we will going to put the value of E, Planck constant, H, for pi value, mass of electron and velocity of light. Then it will going to give us the value of beta, that is Bohr magneton, as 0.92731 into 10 raised to minus 20 arc Gauss inverse. We are discussing two sources of paramagnetism, in which orbital we have discussed. Now spin effect, spin magnetic moment. As we can see, the ratio of orbital magnetic moment, that is E omega square by 2c, and the total orbital angular moment, that is m omega square, is E by 2 mc. For the spinning of electron, the ratio of the spin magnetic moment and the spin angular moment is E by mc. Therefore, we can write that spin magnetic moment, which is represented by mu subside s, is equal to spin angular moment into E by mc, is equal to s into bracket s plus 1 raised to 1 half into h upon 2 pi into E by mc, is equal to 2 into s bracket s plus 1 bracket over whole raised to 1 half into EH by 4 pi mc, is equal to 2 into bracket s plus 1 bracket over raised to 1 half into beta. Beta is equal to EH by 4 pi mc Bohr magnetron, where S stands for the spin quantum number, that is having value plus half minus half. This equation 1.13, which is there in the above slide, and 1.14 are often written as mu L, that is magnetic orbital magnetic moment, is equal to G into L bracket L plus 1 raised to 1 half into beta, where G is equal to 1, and mu subside S, that is spin magnetic moment, it is represented as G into bracket S plus 1 raised to 1 whole raised to 1 half into beta, where G is equal to 2, where G represents the gyromagnetic ratio. Please remember, this is a corner question, where G represents the gyromagnetic ratio, the ratio of spinning magnetic moment mu subside S to the spin angular moment S into bracket S plus 1 raised to 1 half corresponding to it. Now next point, that is diamagnetism and Pascal's constant. A diamagnetic substance has no permanent magnetic dipole. Therefore, when a magnetic field is applied to it, no interaction tending to bring about an alignment of the magnetic dipole with the field take place. However, the substance experiences a repulsion from the applied field. Let us consider an electron moving about the nucleus in orbit. We can see in the figure next. When this moving electron is subjected to an external magnetic field, that is applied field H, the electron continues to move in the orbit, but the orbit as a whole process about the direction of the applied field H. So here you can say that this is the applied field H, electron is moving, will now shift it to the applied field H with radius which is R, now converted into R1. This is the precession of electron which moves from here to here, moving. This is orbital motion, but when it is placed into a magnetic field, it get little bit processed on and gives this application of magnetic field on the substance will give rise to the motion of the electron from this directional. It moves in this way, so the radius R converted into R1. In essence, the orbit normal describes a cone of radius R1, while the radius of the orbit is R, which already we have seen in the picture in this slide before, this one. R converted into R1. R1, that is the radius of the cone, and R is the radius of orbit. It has been shown that this processional, this movement from R to R1 has angular velocity, and it is represented as EH by 2mc. Effectively, the electron acquires a new orbital motion which is forced on it by the external magnetic field. In conformity with Lenz's rule, which predicts the direction of motion of a current carrying conductor placed in a magnetic field, the direction of this induced processional magnetic field, that is moved magnetic field on the applied direction, is opposite to that of the applied field. This effect is therefore expressed with a negative sign. It should be noted that the processional velocity becomes zero when the applied field is zero. That is obvious. Thus, the diamagnetic moment due to one electron can be expressed as delta mu is equal to minus E into processional angular velocity into R1 square by 2. So E minus charge is there. E into EH, so processional angular velocity, that is EH upon MC 2mc, R square into 2c, and that is represented as minus E square HR1 square upon 4mc square, where R1 square is the main square radius of the processional orbit described by the origin orbit normal. Let me show you. Yes, this is orbital normal and this is processional orbit, and that has value radius r1. So that r1 square is there. So where r1 is the mean square radius of the processional orbit described by the orbit normal. If the coordinates of the electrons are x, y and z Cartesian coordinates with the nucleus as the origin, that means nucleus in the center, and from that center x, y and z direction is there, then for a time average we have r square is equal to x square plus y square plus z square. So that indicates three-dimensional movement of the electron in space. To find r1 square, we consider the xy plane, only one direction. The z-axis being coincident with applied magnetic field H, so it is neglected. Let us consider a large number of orientation of the orbit. Since all orientations are equally probable, the mean value of the squares of the coordinates along all three axes will be equal. Further, since we are considering the projection of the electron orbit perpendicular to the applied field, we have generic value, that is r square is equal to x square plus y square 2 by 3 x square plus y square plus z square, that means 2 by 3 into r square. Therefore, delta mu is equal to minus e square h r1 square upon 4 mc square is equal to minus e square h r square, that is normal orbit, by 6 mc square. For a multi-electron atom, we have dimagnetic moment represented as mu di atom is equal to minus e square h upon 6 mc square into sigma r square for a multi-electron system. For a gram atom, we can get the value of dimagnetic moment gram atom is equal to minus n e square h upon 6 mc square into sigma r square, where n is the Avogadro's number. To derive the molar diamagnetic susceptibility, we follows xi m dimagnetism is equal to xi z, that is gram magnetic susceptibility. This is molar magnetic susceptibility of a diamagnetic material is equal to gram magnetic susceptibility into m. M is the molar mass of the substance, and that is equal to xi v by rho into m. That is equal to xi v into v is equal to I by H. Xi, that is the magnetic susceptibility, that is intensity divided by applied magnetic field into unit volume, and that is equal to magnetic moment into V by V into H is equal to magnetic moment divided by the applied field. So dimagnetic moment gram for gram atom by H is equal to minus n e square by 6 mc square into sigma r square. A similar relation holds true for the spinning electron and for the spinning nucleus. The electron spin and the nuclear spin hardly affect the diamagnetism of the orbiting electron because the nucleus has a mass much greater than that of the electron, and the spinning electron has much too small a radius, that is approximately 10 raised to minus 13 centimeter, as compared to the radius of orbit, that is approximately 10 raised to minus 8 centimeter. Note the following points about the dimagnetic susceptibility, that is xi di. It is a negative. It opposes the applied magnetic field. It is an inherent property of a substance containing paired or unpaired electron. However, it can be usually detected in a compound containing paired electrons. The unpaired electron being paramagnetic overshadow dimagnetism. Third point, it is independent of both applied field and temperature. It is an induced effect and exists as long as the applied field lasts long. It depends on the magnitude of radius r. The larger the radius of the electron's spin orbit, the greater its magnitude will be. A slight variation in the diamagnetic moment value with a change in temperature has to be viewed in the light of expansion or contraction in the electron orbit. Now, next point we need to discuss, that is Pascal constant and consecutive corrections. Although equations for diamagnetism give an idea of diamagnetic susceptibility, in practice it is of little value because of the uncertainty involved in evaluating the electron orbit radius. Pascal carried out precise calculation of diamagnetic susceptibility of a host of diamagnetic compounds. On the basis of his results, he expressed the molar diamagnetic susceptibility of a compound as Xi m, that is molar diamagnetic susceptibility is equal to sigma Na into Xi a is equal to sigma lambda, where Xi represent the gram atomic susceptibility of atom A, Na that represent is the number of atom A in the molecule, and lambda is the consecutive correlation for certain bond type. Here not gram, but it's a molar magnetic susceptibility. We can take an example for Pascal's work to show how he found out the value of Xi c. Aliphatic series, value of Xi m and its difference. Hexane 79.6 into 10 raised to minus 6, there is no difference. Octane 103.7 into 10 raised to minus 6, and the difference would be 2 into 12.05 into 10 raised to minus 6. Decane 129.7 into 10 raised to minus 6, that is the molar magnetic susceptibility, and the difference would be 2 into 13.0 into 10 raised to minus 6. Aromatic series, benzene have value of magnetic susceptibility, molar magnetic susceptibility, that is 57.4 into 10 raised to minus 6, and there is no difference. Toluene has 69.9 into 10 raised to minus 6, and the difference would be 12.5 into 10 raised to minus 6. And M-xylene, that is C6H4CS3 twice, metaxylene, that is 82.1 into 10 raised to minus 6, and the difference would be 2 into 12.35 into 10 raised to minus 6. From this data, the mean value of the methyl group is obtained, that is minus 12.35 into 10 raised to minus 6. Then Xi c, that is the concentration of the magnetic susceptibility, is represented as Xi CH2 minus Xi H, that is hydrogen. So that value, when we will going to subtract from this, we're going to get the value for CH2 magnetic susceptibility for methylene group, that is minus 6.25 into 10 raised to minus 6 erg CGS centimeter unit. The value of Xi H magnetic susceptibility of applied field was obtained independently from the measurement on the hydrogen. Pascal constants for some atoms are given in the table we will going to see in the next slide. Pascal also realized that for certain bond type, his experimental data fitted well with his empirical equation, that is Xi m, that is molar magnetic susceptibility of dimagnetic material, is equal to summation sigma Na into Xi a is equal to sigma lambda. Only when he introduced certain corrections, we can see in the table. That correction is given in this table. Pascal atomic constant psi a and Pascal consecutive corrections lambda. So for hydrogen, magnetic susceptibility of a dimagnetic material, that is minus 2.93, and atoms or ion species, that is fluoride, has value minus 6.3. So these are the different values. Here you can see that aldehyde or ketone have plus value and rest other compounds or elements and atoms have minus value of dimagnetic susceptibility. Now atom and bond in carbon in ring structure of a carbon have magnetic susceptibility, dimagnetic susceptibility minus 0.24, and carbon shared by two rings, that is C double bond C, C triple bond C, C double bond N, C double bond triple bond N double bond and N double bond O, all are having positive value of magnetic susceptibility of dimagnetic substance. Thus, in the compound containing the carbon-carbon double bond, he observed that the molar dimagnetic susceptibility value based on atom constant had to be corrected by plus 5.5 into 10 raised to minus 6 CGS units to get a good fit with the experimental values. Similarly, the compound containing the C double bond C bonds had to be corrected by plus 0.8 into 10 raised to minus 6 CGS units. The dimagnetic susceptibility of some common ions and the molecule experimentally obtained are listed in this table 1.4. So this is the experimental value obtained for this different type of ions and this different type of ligands or compound, and that is experimentally obtained data for dimagnetic susceptibility. Now how to calculate? Calculation of Xi, that is magnetic susceptibility for pyridine and acetone. Pyridine C5H5N, sum of contributions of Xi into 10 raised to minus 6, that you need to consider cube mole inverse. 5 into C of the ring, and ring value in the previous table we found that it is minus 6.24. Let's see in the table for carbon. Yes, carbon minus 6 and carbon in a ring minus 24. So 6.24. So that is how the value of carbon in the ring is obtained, and that is multiplied 5 times because C5 is there. So we are getting minus 31.2, and for hydrogen 5 into H value, that is minus 2.93. So we're going to get minus 14.6, and one nitrogen. So nitrogen of a ring and nitrogen outside the ring have two different value. So nitrogen of a ring have minus 4.61. So that is multiplied with 1, we're going to get minus 4.6. Now combined together, Xi is equal to sigma I xai or into x sigma I x bi is equal to, so addition of this and this will gives us 50.4 into 10 raised to 6 semi-cube mole inverse. So the functional groups are accounted for by using ring values for carbon and nitrogen. So sigma I xi bi equals to 0. This is considered to be 0. Now acetone, that is CH3 twice C double bond O, sum of the atom contribution into 10 raised to 6 centimeter cube mole inverse. Carbon 3, and that is not of a ring, it's of a chain, and that is why it is get this value minus 18.0. Hydrogen into 6 gives 17.6 minus 17.6, and one oxygen, that is minus 4.6, and that is outside ring as well. So some of the bond contribution, if we are going to apply for this acetylenic group, we're going to get minus 33.9 into 10 raised to minus 6 semi cube mole inverse. Now, utility of Pascal constant, our last point of today's lecture. We often come across a ligand which can be directly synthesized and isolated. The diamagnetic susceptibility of such a ligand can be directly measured. However, there are ligands which cannot be directly synthesized and isolated. Such a ligand can be synthesized in the form of a metal complex by the metal ion promoted template reaction. For example, the skip base salicylic glycine has not been isolated so far. However, its complex can be synthesized by reacting a metal acetate with salicylic and glycine in aqueous alcohol. Also, the N4 macrocyclic ligand tetra hydroaminobenzaldehyde could be had only in the form of its transition metal complexes, that is nickel 2 complex, via self condensation of O-aminobenzaldehyde. To calculate the diamagnetic susceptibility of these ligands, the only alternative is to draw from Pascal's constant and constitutive corrections. Well, this is enough from my side. If you have